In this lecture, we'll describe how the continued fraction expansion of a number is connected with our earlier quest to find excellent rational approximations to real numbers. In fact, we'll see how truncating the continued fraction of a real number produces the world's best rational approximations to that number. In particular, we'll see that this algorithm generates the so-called best rational approximates, the existence of which, as we saw in lecture 21, was foreshadowed in the work of Johann Dirichlet. We'll then return to the musical conundrum we offered in our discussion of geometric progressions at the opening of this course, and at long last, using these ideas from Diophantine approximation, see why we have adopted a 12-note chromatic scale. We've seen earlier in this course that the decimal expansions for quadratic irrational real numbers will never become periodic because those numbers are irrational. Instead, we see a chaotic-looking jumble of digits without any easily identifiable structure or pattern. In this lecture, we'll discover some remarkable periodic patterns that only come into focus when we consider the continued fraction expansions of these quadratic irrationals. Miraculously, this beautiful structure can be exploited to find all natural number solutions to the Pell equations that we studied earlier in our sojourn into Diophantine equations. Of course, there always are remaining unanswered questions, and we'll close this lecture with some famous vexing open questions involving continued fractions. Well, let's open this lecture by returning to Johann Dirichlet's theorem that we discussed in lecture 21. Dirichlet's theorem asserts that for any real number alpha and any natural number capital Q greater than 1, we can find a rational number p over q with the property that the denominator q is greater than or equal to 1, but less than or equal to the capital Q, and that p over q is relatively close to alpha. Specifically, we have that the distance between alpha and p over q, measured by the absolute value of alpha minus p over q, is less than or equal to 1 over capital Q plus 1 times little q. Throughout the previous 2 lectures, we've been concerned with how well a rational number approximates a real number alpha relative to the size of the denominator of the rational approximant. One way to measure this delicate balance between denominator size on one hand and the quality of approximation to alpha on the other is just to multiply the denominator by the distance between the rational number and alpha. In other words, we could study the quantity q times the absolute value of alpha minus p over q, which if you imagine distributing that q in, we'd see alpha q and then minus p, since p over q times q would just give us p. So the quantity that we now want to study is the absolute value of alpha times q minus p. In some sense, this value is a weighted measure of how well p over q approximates alpha, weighted in the sense that we're weighting it against the size of the denominator. By Dirichlet's result, we see that the rational p over q appearing in his theorem satisfies the inequality. The absolute value of alpha q minus p is less than or equal to 1 over capital Q plus 1. And let's notice that as capital Q gets larger and larger, then 1 over capital Q plus 1 gets smaller and smaller and is, in fact, approaching 0. So by Dirichlet's theorem, the absolute value of alpha q minus p is approaching 0 as well. If we now assume that alpha is irrational, then as we allow capital Q to take on larger and larger values without bound, we can generate an endless list of rational numbers, and I'll call them P1 over Q1, P2 over Q2, P3 over Q3, and so on, and they satisfy the following string. The absolute value of alpha Q1 minus P1 is larger than the absolute value of alpha times Q2 minus P2, which in turn is actually larger than the absolute value of alpha Q3 minus P3, and so on. These quantities are ever shrinking towards zero. Well, these rational numbers thus offer a very good approximation to alpha relative to their denominators. These weighted measures are getting smaller and smaller. Well, these observations lead to a new notion, that of the best rational approximations to an irrational number alpha. Given an irrational number alpha, we define the best rational approximations to alpha to be the complete list of rational numbers P1 over Q1, P2 over Q2, P3 over Q3, and so on, that satisfy that inequality we just saw. Absolute value alpha Q1 minus P1 is larger than absolute value alpha Q2 minus P2, which in turn is greater than the absolute value of alpha Q3 minus P3, and so on. Well, in 1770, the French mathematician Joseph Lagrange proved a truly amazing and beautiful result. He showed that the list of best rational approximations is precisely the list of rational numbers found by truncating the continued fraction expansion for alpha. Thus, the continued fraction expansion of a real number holds an incredibly important secret: the number's best rational approximations. Isn't that great? So, if we wish to find the very best rational approximations of a real number alpha, we need only consider the fractions generated by truncating alpha's continued fraction expansion. For example, if we return to the golden ratio, 1 plus square root of 5 all over 2, which has the endless continued fraction of all just ones, so writing it in shorthand, we just would see 1, 1, 1, 1, 1, and so forth, which remember means 1 plus 1 over, 1 plus 1 over, 1 plus 1 over, but we abbreviate as just 1, 1, 1, 1. Well, then the best rational approximates to this special number are precisely those rationals having continued fractions just 1, 1, 1, 1, 1 with a final 1 someplace. Well, we've already seen that these fractions are precisely the ratios of two consecutive Fibonacci numbers, the larger to the smaller. So we see the synergy between the Fibonacci numbers and the golden ratio in full bloom. Magnificent. Well, moving from the beauty of what we see to the harmony of what we hear, we now return to our discussion of musical geometric progressions. In Lecture 4, we defined an octave as a musical interval between two pitches in which the two pitches have frequencies in a ratio of 2 to 1. An interval is a perfect fifth if the ratio of the frequencies of the two pitches is 3 to 2. Now, in Western music, the chromatic scale begins at one pitch, let's say A, and progresses up in what are called half steps until it reaches the note that is 1 octave above the starting pitch. These pitches are derived from a geometric progression of perfect fifths, starting with the first pitch and having a ratio of R, which is 3 halves. For example, if we start at A, the note A, which is 440 hertz, we would produce 440, then 440 times 3 halves, then 440 times 3 halves squared, then 440 times 3 halves cubed, then 440 times 3 halves to the fourth, and so on. That would be the geometric progression we would produce. In other words, we'd see the numbers 440, 660, 990, 1485, 2227.5, and so on. Well, of course, you can see that these pitches are getting very, very high, and probably only our pets could hear them. So in order to keep the notes within the 440, 880 hertz range, we divide the frequencies by 2 in order to lower the pitches so that they fall into the correct octave. Well, this process requires us to modify our attractive geometric sequence. Well, we're now in a position to answer the fundamental question. Why do we end up with a 12-note chromatic scale? Well, once we factor out the 440, the terms in our geometric progression have the form 1, 3 halves, 3 halves squared, 3 halves cubed, 3 halves to the fourth, and so on. However, remember that we also repeatedly divide by 2 as necessary. In other words, we divide by powers of 2 to attain our goal, to return to the same note but 1 octave higher. Thus, we want to find a natural number exponent q and another natural number exponent p so that 3 halves raised to the q power, all divided by 2 to the p power, is ideally 1, or at least very, very close to 1. Why is that? Well, because the 3 halves to the q represents the progression, but we have to keep dividing by 2 as necessary, and therefore we divide by 2 to some power p, and we want to bring that back down to where we started, and we started with 1, so we want to get as close to 1 as possible. Now, notice that the q represents the number of notes in the scale that we're constructing, because remember, that tells us where we are in this sequence. So, phrased a bit more mathematically, we wish to find natural numbers p and q so that 3 halves to the q divided by 2 to the p is approximately equal to 1. Now, this is equivalent to having 3 halves to the q approximately equal to 2 to the p. And so we could write this out. We could say 2 to the p is approximately equal to 3 halves to the q. Now, notice that p is the exponent we have to raise 2 in order to approximately equal 3 halves to the q. So our approximation can be translated into an equivalent statement involving a logarithm. Because remember, a log is an exponent. And so what we see here is that p is the exponent to which we have to raise 2 in order to see 3 halves to the q power. And so that translates into p is approximately log of base 2 of 3 halves to the q power. I just took that approximation and now wrote it as the identical approximation using a log. And also, using properties of logs that we saw earlier, this actually equals q times log base 2 of 3 halves. So that q exponent can be pulled out as a coefficient. Well, dividing now both sides of this approximation by q, we see that p over q is approximately equal to log base 2 of 3 halves. In other words, we see that finding the length of the chromatic scale is equivalent to finding an excellent rational approximation, p over q, to the number log base 2 of 3 halves. We've come full circle. Well, now remember that q, the denominator, represents the number of notes in our scale. Well, we now know exactly how to proceed. We first find the continued fraction expansion for log base 2 of 3 halves, and then truncate the expansion to generate its best rational approximations. Well, using the decimal expansion log base 2 of 3 halves, which works out to be 0.58496 and so forth, and a calculator, we can compute the first few terms of the continued fraction expansion. And the first few partial quotients of log base 2 of 3 halves are 0, 1, 1, 2, 2, 3, 1, 5, 2, 23, and so on. Of course, doesn't seem to be any particular pattern here. Well, we can now find the best rational approximations by merely truncating this expansion. And this truncation process generates the rational numbers that are the best approximates. For example, if we truncate at the very beginning, we'd see 0 over 1, which of course is 0. If we truncate at after 0, 1, then we just have 1 over 1. If we truncate after 0, 1, 1, we'd end up seeing a half. Then we'd see 3/5. Then we'd see 7/12. Then we see 24 41sts, and so on. Well, now let's recall that the denominators represent the number of notes in our chromatic scale. We also recall that our approximation P over Q should make 3/2 to the Q divided by 2 to the P close to 1. Well, if we consider the approximation 7/12, then we can use a calculator to discover that 3/2 to the 12th power divided by 2 to the 7th power equals 1.013 and so forth, which is indeed very close to 1. 1.013 something is very, very close to 1. So a 12-note chromatic scale would bring us very nearly to our starting note, but 1 octave higher. And that 12 in the denominator of the best approximate is the same 12 that gives us the 12-note scale. Well, of course, we could get even closer to 1 by using the approximation 24 over 41. But that would then require a 41-note scale, which would not be practical. I mean, imagine the size of the pianos. Woo! Really, really long. So the 12-note chromatic scale is the standard. And that 12, we now see, is the denominator of a best rational approximation. Music and number theory harmoniously unite. Well, the reality that 3/2 to the 12 divided by 2 to the 7th equals 1.013 something rather than exactly 1 is one of the reasons why tuning musical instruments, such as pianos, is so daunting and difficult. Well, the next time that you are at a concert and you're hearing the notes wash over you, remember that there are continued fractions and more generally number theory lurking behind the scenes. Well, now that we have a newfound appreciation for the number theory hidden within our Western music, I want us to return to quadratic irrationals and discover structure hidden within these ancient numbers. Let's first recall that quadratic irrational numbers are irrational numbers that are also solutions to quadratic equations having integer coefficients, such as 4x squared minus 3x plus 5 equals 0, or more generally, ax squared plus bx plus c equals 0 for some given integers a, b, and c. As we've already seen, the square root of 2 is a quadratic irrational, because it's a solution to x squared minus 2 equals 0. The golden ratio, 1 plus square root of 5 over 2, is a quadratic irrational because it is a solution to the quadratic x squared minus x minus 1 equals 0, as we've seen several times before. Notice that such irrationals always involve simple square roots. We've also computed the continued fraction expansion for each of these quadratic irrational numbers, and we found that the square root of 2 has a continued fraction consisting of 1 and then a repeated list of 2s. So 1, 2, 2, 2, 2, 2, 2, which remember means that the square root of 2 equals 1 plus 1 over, 2 plus 1 over, 2 plus 1 over, 2 plus 1 over, and so forth endlessly. And for 1 plus the square root of 5 over 2, we saw all 1s. So 1 plus 1 over, 1 plus 1 over, 1 plus 1, 1, endlessly. In each case, we've noticed that the continued fraction eventually becomes periodic. So, does this periodic pattern within the continued fraction hold for other quadratic irrational numbers? It's a good question. Well, how do we build some insight? Well, we build insight into this question by considering continued fraction expansions for some other quadratic irrationals and see what we see. So we'd use a calculator to do this, and we could actually confirm using a calculator that the square root of 3 has a continued fraction that consists of 1, 1, 2, 1, 2, 1, 2, 1, 2 forever, and so on. The square root of 5 has a continued fraction that begins 2, 4, 4, 4, 4, and so on. Square root of 6 begins 2, 2, 4, 2, 4, 2, 4, and so on forever. Square root of 7 begins 2, 1, 1, 1, 4, 1, 1, 1, 4, 1, 1, 1, 4, and so on forever. And even a number like the square root of 23 begins 4, 1, 3, 1, 8, 1, 3, 1, 8, 1, 3, 1, 8, and so on forever. Notice that in all these examples, the continued fraction expansion we find is indeed periodic. In fact, this observation holds in general for any real quadratic irrationals. This proposition was first established by Joseph Lagrange at the same time he proved his best rational approximation theorem in 1770. This result is now known as Lagrange's theorem and states that a real number has a periodic continued fraction expansion if and only if the real number is a real quadratic irrational number. For example, if we consider the very complicated looking quadratic irrational 4 minus the square root of 19 divided by 3, then if we looked at its continued fraction expansion, we would see negative 1, 1, 7, 2, 1, 3, 1, 2, 8, 2, 1, 3, 1, 2, 8, and so forth. And we would notice that it too is periodic with the endless repetition of 2, 1, 3, 1, 2, 8 forever. Let's now return to the simple quadratic irrationals of the form just square root of d for some natural number d that's not a perfect square. And let's look at the continued fraction expansions a little bit more closely. Upon closer inspection, we notice something amazing. And in fact, there's some incredible coincidences that we can't help but notice. For example, the last number appearing in the repeated period always equals 2 times the first partial quotient. Moreover, if we consider the period without that last term, so remove that last term from the period, we'd see that the number list that we have does not change if we read it backwards or forwards. In other words, the period without that last term is a numerical palindrome. Well, to illustrate these observations, let's return to the square root of 23, which we saw had a continued fraction that began 4, 1, 3, 1, 8, 1, 3, 1, 8, and so on. And notice that the last number in the period is 8, which indeed is twice the first number 4. And also, the period with the last 8 removed is, in fact, 1, 3, 1. Indeed a palindrome. Read it backwards. 1, 3, 1. By the way, my favorite palindrome is Ed is on no side. Think about it. Anyway, these amazing coincidences are, in fact, theorems. In particular, if d is a natural number that's not a perfect square, the continued fraction for the square root of d will always become periodic after the very first partial quotient. The last number in the period will always be twice the first partial quotient, and the period with the last number removed is always a palindrome. Truly remarkable, truly beautiful. In fact, it gets even better. Because we can connect this amazing structure within the continued fraction expansion of the square root of d with the Pell equation we studied in lecture 13. Let's recall that the Pell equation has the generic form x squared minus dy squared equals 1, for which d is a given natural number that's not a perfect square. For example, x squared minus 2y squared equals 1 is a specific Pell equation. As with any Diophantine equation, we seek integer solutions. In this case, we want natural number solutions to this equation. We'll study the specific Pell equation x squared minus 2y squared equals 1 to illustrate a much more general theory at work. If we factor the left-hand side of this equation, then our equation becomes x minus the square root of 2 times y multiplied by x plus the square root of 2 times y, all equals 1. If we now divide both sides by the second factor we see, then we'd see that x minus the square root of 2 times y equals 1 over x plus the square root of 2 times y. And just for the sake of seeing the big picture, let's not worry about the details. So imagine squinting your mathematical eyes for a little bit and let things blur a little bit. We see that, let's assume that, in fact, the size of x is roughly speaking the size of y. And we can make that precise, but we won't. So roughly speaking, we can say that x minus the square root of 2 times y is approximately equal to 1 over, and instead of the x, let's just put a y plus square root of 2y. Which, if we divide both sides by the y, we see x over y minus the square root of 2 is approximately equal to 1 over the quantity 1 plus the square root of 2 times y squared. And if we take the absolute value of both sides and introduce a little inequality by throwing away that number 1 plus square root of 2, then we'd come upon the perhaps familiar-looking inequality, the absolute value of x over y minus the square root of 2 is less than 1 over y squared. An inequality that we actually saw earlier in lecture 21 that's satisfied by all the best rational approximations to the square root of 2. Thus, perhaps the solutions x and y that we seek to the Pell equation, x squared minus 2y squared equals 1, come from the continued fraction expansion for the square root of 2. We recall that the continued fraction for square root of 2 is 1 and then an endless run of 2's. And computing the best rational approximations by just truncating the continued fraction, we'd actually see the list of best rational approximates, which work out to be 1 over 1, 3 over 2, 7 over 5, 17 over 12, 41 over 29, 99 over 70, and so on. If we consider these fractions as x over y, and then compute x squared minus 2y squared, we see something totally astounding. 1 squared minus 2 times 1 squared equals negative 1. 3 squared minus 2 times 2 squared equals 9 minus 8, which equals 1. 7 squared minus 2 times 5 squared equals 49 minus 50, which is negative 1. 17 squared minus 2 times 12 squared equals 289 minus 288, which is 1. 41 squared minus 2 times 29 squared is 1681 minus 1682, which is negative 1. 99 squared minus 2 times 70 squared equals 9801 minus 9800, which equals 1. In other words, every other best rational approximation gives rise to a solution to the Pell equation. And the other approximations give rise to the solution to the related Pell equation, x squared minus 2y squared equals negative 1. We get them for free. Well, in fact, a version of this phenomenon holds in general. To find all natural number solutions to the Pell equation x squared minus d times y squared equals 1, we first compute the continued fraction of the square root of d, and then compute the rational numbers formed by truncating the continued fraction right at the end of the palindromic part. In other words, right before the last term of the period. Those rational numbers we generate, x over y, will give us the complete list of all natural number solutions xy to the Pell equation, x squared minus dy squared equals 1. Now, while we won't prove this assertion here, we do certainly celebrate the incredible number-theoretic structure captured within continued fraction expansions and the remarkable amount of information those expansions hold. Of course, there's plenty we don't know about continued fractions. Recall that we've seen that the continued fraction expansions for quadratic irrational real numbers are eventually periodic. We now wonder if there are other patterns in the continued fractions for other types of numbers. Let's take a look at how the continued fraction expansion for pi begins. Well, here we're seeing a whole bunch of the partial quotients, and do we see a pattern? We see 3, 7, 15, 1, 292, 1, 1, 1, and so on. Well, clearly there's no obvious pattern. Let's just look at the largest values seen so far as we scan down that list of natural numbers. We see first the 3, then the 7, then the 15. The next biggest one will be 292. Then if we scroll down a little further, we'd see 436. And if we just go a little bit further, we see the whopping 20,776. Will these largest values get arbitrarily large? Or is there a limit to their size? In other words, are there numbers in the partial quotient, are these numbers in the partial quotients of pi bounded, or are those numbers unbounded? Well, this question remains a notoriously difficult open question, although the conjecture is that these numbers grow without bound. Well, perhaps the chaotic-looking nature of the partial quotients of pi arise from the fact that pi is transcendental. Well, to test this theory, let's consider the number cube root of 2, which is algebraic and thus not transcendental, because it's algebraic because it's a solution to the cubic equation x cubed minus 2 equals 0. Well, because the number is a cube root and not a square root, it's not a quadratic irrational, so we know that its continued fraction does not repeat. But perhaps there's a different type of easy pattern to uncover. Well, let's take a look at the first few partial quotients in the continued fraction for the cube root of 2. And we'd see 1, 3, 1, 5, 1, 1, 4, 1, and so on. You see a pattern? I don't. In fact, it appears just as chaotic looking as that of pi. If we again just keep track of the largest values that we see as we look down those partial quotients, we'd see 1, then 3, then 5, then 14, 15, and then if we wait a little bit longer, we see 534. Is there a largest value in this list? In other words, are these numbers associated with the cube root of 2 bounded or unbounded? No one knows. Again, this remains a notoriously challenging open question. The conjecture is that these numbers grow without any bound whatsoever, but nobody can prove or disprove this claim. In both the continued fraction expansion for pi and for the cube root of 2, we see that the number 1 appears more often than any other number. Well, this observation turns out to be a much more reasonable insight in light of a much deeper result about continued fractions, and we'll actually describe these results in our final lecture. So continued fractions, you can now see, beautifully come into fruition through many, many different types of applications, through music, through Diophantine equations, and I hope that I've won you over with continued fractions.